Of all humanity's inventions, few have been as transformative as the wheel. It seems so simple, so obvious, a circular object that rotates around an axis. Yet the wheel didn't exist in nature in any useful form. No animal evolved wheels. No plant grows them. The wheel is purely a product of human imagination and ingenuity, and its invention fundamentally changed the trajectory of human civilization. This is the story of how a simple circular shape reshaped the world. Origins and early innovation. The wheel first appeared around 3500 BCE in ancient Mesopotamia, in the region between the Tigris and Euphrates rivers, in what is now modern-day Iraq. This area, often called the cradle of civilization, had already given humanity agriculture, writing, and urban settlements. The wheel would be yet another revolutionary contribution from this fertile crescent. But here's what's fascinating. The wheel's first use wasn't for transportation at all. The earliest wheels we know of were potter's wheels, used for shaping clay into pottery. Archaeological evidence from Mesopotamian sites shows potter's wheels predating wheeled vehicles by several centuries. These early potter's wheels were simple, a flat disc that could be rotated, allowing potters to shape clay vessels with unprecedented symmetry and speed. This makes sense when you think about it. A potter's wheel doesn't need to bear heavy loads or travel over rough terrain. It just needs to spin smoothly. This simpler application allowed early craftsmen to perfect the concept of a rotating disc before tackling the more complex challenge of making a wheel that could support weight and move across the ground. Before the true wheel emerged, early humans had already discovered the principle of rolling. They observed that heavy objects could be moved more easily if placed on top of cylindrical logs. As the object was pushed forward, it would roll over the logs. When a log emerged from the back, workers would carry it to the front and place it under the leading edge, creating a continuous rolling path. This technique was used to move massive stones for construction, to transport heavy loads, and to accomplish tasks that would otherwise require enormous manpower. The pyramids of Egypt, built before wheeled vehicles were common in that region, were likely constructed using this log rolling technique for moving the massive stone blocks. But rolling logs had limitations. You needed many logs, constant repositioning, and relatively flat terrain. The logs themselves could crack or split under heavy weight, and the process was labor-intensive, requiring multiple workers to manage the logs while others pushed the load. The conceptual leap from rolling logs to the wheel was profound. Someone had to imagine separating the rolling cylinder into two parts, two wheels connected by an axle, with the load suspended between them on a platform. This required understanding that the wheel didn't need to be a full cylinder, that it could be a disc, and that two discs connected by a fixed axle could roll continuously without needing to be repositioned. This might seem obvious to us now, but at the time it represented a significant mental breakthrough. The wheel might have existed in concept form long before it was actually built, passed down through generations as an idea, refined mentally before someone finally had the tools and materials to make it reality. Think about what this required. Understanding circular motion, grasping the relationship between the wheel and axle, recognizing that the axle must remain fixed while the wheels rotate around it, and solving the engineering challenges of creating a bearing surface that would allow smooth rotation without excessive friction. The invention of the wheel showcases human ingenuity at its finest, the ability to observe natural phenomena, abstract principles from those observations, and then create something entirely new that doesn't exist in nature. First transport wheels. Around 3000 BCE, roughly 500 years after the potter's wheel appeared, Mesopotamians adapted the wheel concept for transportation, creating the first wheeled vehicles, carts and wagons that would transform human society. These early transport wheels were solid wooden discs, often carved from a single piece of wood or made from planks fastened together. They were heavy. A single wheel might weigh 50 pounds or more. But they were also durable and relatively simple to manufacture with the tools available at the time. The wheels were attached to a fixed axle, meaning the axle and wheels rotated together as a single unit beneath the cart. The cart body rested on the axle through a bearing surface, allowing the entire wheel and axle assembly to spin while the cart remained stable. This design was simple but effective. The impact was immediate and profound. Suddenly, a single ox or donkey pulling a wheeled cart could transport loads that previously required multiple pack animals or many human porters. A cart could carry several hundred pounds of goods, grain, or materials, moving them faster and with less effort than any previous method. This enabled heavier loads to be transported regularly. Farmers could bring more produce to market. Builders could move construction materials more efficiently. Merchants could transport goods in bulk rather than small quantities on pack animals. Longer journeys became feasible. Before wheeled vehicles, long-distance transport was limited by how much a human or animal could carry on their back over multiple days. With carts, the same animal could pull many times its carrying capacity, making longer trade routes economically viable. Trade expansion followed naturally. Cities that were previously isolated by distance could now exchange goods regularly. Regional economies became connected. Specialization increased as communities could trade their surplus production for goods they couldn't produce locally. What's particularly interesting is that some early wheels featured decorative carvings. Archaeological finds show wheels with geometric patterns, symbols, and even religious imagery carved into their surfaces. This reveals something important about human nature. Even with purely functional technology, we felt compelled to add aesthetic elements. These decorated wheels show that technology and art overlapped from the very beginning. The wheel wasn't just a tool. It was an expression of craftsmanship and culture. A well-made, beautifully carved wheel might indicate the owner's wealth or status. It might serve ceremonial purposes or carry religious significance. This pattern would repeat throughout history. Humans rarely create purely functional objects. We decorate our tools, embellish our weapons, and turn utilitarian items into works of art. The decorated wheels of ancient Mesopotamia were early examples of this fundamental human impulse. Early wheels spread rapidly across the ancient world. From Mesopotamia, wheeled vehicles appeared in the Indus Valley, the Caucasus region, and eventually Europe. Each culture adapted the basic concept to their needs and available materials. In forested regions, Wheels were often carved from solid sections of tree trunks. In areas with less timber, planks were fastened together. Some cultures developed wheels with a slight dish shape, providing better stability on uneven terrain. The axle technology also evolved. Early fixed axles gave way to axles that could rotate independently within hubs, reducing friction and wear. Lubrication, initially animal fat, later plant oils, was applied to axle bearings to ensure smooth rotation. Material and design evolution. Around 2000 BCE, roughly 1,000 years after solid wheels appeared, someone invented the spoked wheel, an innovation that would prove as revolutionary as the wheel itself. The spoked wheel replaced the solid wooden disc with a rim connected to a central hub by multiple spokes radiating outward like the rays of the sun. This design was dramatically lighter. A spoked wheel might weigh a quarter or a third as much as a solid wheel of the same diameter, while maintaining structural strength. The weight reduction had enormous implications. Lighter wheels meant vehicles could move faster with the same pulling power, or maintain the same speed with less effort. This made wheeled vehicles practical for applications beyond slow-moving cargo transport. The development of spoked wheels likely came from observing natural structures. Think about tree branches radiating from a trunk, or the way spider webs distribute force through radial threads. These natural patterns demonstrate how a few well-placed structural elements can provide strength without solid mass. Ancient engineers recognized that a wheel doesn't need to be solid throughout. The structural forces, the weight pressing down, and the torque from acceleration could be handled by strategically placed spokes. The space between spokes didn't need to support anything, so it could be removed, saving weight. Early spoked wheels typically had 4 to 8 spokes, usually made from carved wood, selected for strength and flexibility. The spokes connected the rim to a central hub, which housed the axle bearing. The rim itself was often made from multiple segments of bent wood, steamed and shaped into a circle, then fastened together. Creating a spoked wheel required significantly more skill than making a solid wheel. Each spoke had to be precisely shaped and angled. The rim segments had to form a true circle. The hub had to be strong enough to handle the forces transmitted through the spokes. This was sophisticated carpentry, requiring specialized knowledge and tools. But the benefits justified the effort. Spoked wheels made fast vehicles practical, leading directly to the development of chariots, light, two-wheeled vehicles pulled by horses that could achieve speeds impossible for heavy cargo wagons. Chariots appeared across multiple civilizations around the same time, suggesting either rapid spread of the technology or possibly independent invention. They became crucial for warfare and racing, applications where speed and maneuverability were paramount. Alongside spoked wheels came innovations in other wheel components. Axle design improved, with better materials and more sophisticated bearing surfaces. Bronze and later iron axles replaced wooden ones, providing greater strength and durability. Hub strengthening became a focus of engineering attention. The hub is where all the forces converge, the weight of the vehicle pressing down through the spokes, the rotational forces from acceleration and braking, and the lateral forces from turning, Making hubs that could handle these forces without splitting or deforming required careful design and quality materials. Metal rims appeared, first as protective strips on the outer edge of wooden rims, later as complete metal hoops. Bronze and iron rims protected the wheel from wear, allowed vehicles to operate on rougher terrain, and increased the wheel's lifespan dramatically. By 1000 BCE, wheel technology had advanced to a sophisticated state. Chariots with delicate spoked wheels, metal-reinforced hubs, and iron-rimmed wheels were being produced across the ancient world, from Egypt to China. These wheels represented the cutting edge of technology, the product of centuries of incremental improvement and refinement. Impact on warfare. The chariot revolutionized ancient warfare, changing battle tactics, military organization, and the balance of power between civilizations. It was the ancient world's equivalent of the tank, a mobile platform that combined speed, mobility, and firepower in a way that foot soldiers couldn't match. Chariots first appeared in warfare around 2000 BCE, shortly after the invention of spoked wheels made light, fast vehicles practical. Early military chariots were simple platforms for two people, a driver who controlled the horses and a warrior who fought from the moving chariot. In Egypt, chariots became central to military power. Egyptian chariots were lightweight, typically pulled by two horses, and carried a driver and an archer. The archer could shoot arrows while moving, engaging enemies from a distance before they could respond. Egyptian tomb paintings and reliefs show chariots prominently, emphasizing their importance to Egyptian military identity. The famous Battle of Kadesh in 1274 BCE, fought between Egypt and the Hittite Empire, involved thousands of chariots on both sides, possibly the largest chariot battle in history. The Egyptians, under Pharaoh Ramesses II, deployed numerous chariot divisions. The battle demonstrated both the power of chariot forces and the importance of tactics and coordination. In Mesopotamia, chariots followed a different design philosophy. Mesopotamian chariots were often heavier, sometimes carrying 3 or 4 people, and were pulled by donkeys or onagers before horses became common. They served as mobile command platforms and shock troops, charging into enemy formations to break their lines. In China, chariots appeared during the Shang dynasty around 1200 BCE and became integral to Chinese warfare for centuries. Chinese chariots were typically pulled by 4 horses and carried 3 people: a driver, an archer, and a spearman or halberd wielder. Chinese military treatises devoted considerable attention to chariot tactics, formations, and maintenance. The Rig Veda, ancient Indian text dating to around 1500 BCE, describes chariot warfare extensively. Indian chariots were important both militarily and symbolically, associated with gods and heroes. Indian charioteers were trained warriors from childhood, representing a warrior elite. Chariots enabled speed that was revolutionary for ancient warfare. While infantry marched at perhaps 3 to 4 kilometers per hour, chariots could travel at speeds of 20 to 30 kilometers per hour, even on ancient roads. Some ancient sources claim chariots could cover 40 to 50 kilometers in a day, an astonishing distance for ancient technology. This speed provided enormous tactical advantages. Chariot forces could outflank enemy armies, pursue retreating forces, raid supply lines, and withdraw before enemies could respond. They could concentrate rapidly at critical points on the battlefield, creating local superiority even against larger forces. Mobility was equally important. Chariots could operate across various terrain types, open plains, river valleys, and even desert fringes. They gave commanders flexibility to respond to changing battlefield conditions, to exploit opportunities, and to avoid unfavorable engagements. The tactical advantages were numerous. Chariots provided elevated fighting platforms, giving warriors better visibility and shooting angles. The psychological impact of charging chariots was significant. The thunder of hooves, the dust, the speed of approach created fear in enemy ranks. Chariots could break infantry formations through shock and momentum. Initially, chariots were tools of the elite. Building a chariot required skilled craftsmen, quality materials, and considerable time. Horses needed to be bred, trained, and maintained, an expensive proposition. Only wealthy nobles or states with substantial resources could field chariot forces. Chariot warriors formed aristocratic military classes in many societies. They trained from childhood in chariot driving and fighting, developing specialized skills that foot soldiers couldn't match. This created a military elite whose power derived from their mastery of chariot warfare. But over time, chariot technology spread and became more accessible. As manufacturing techniques improved and more craftsmen learned the skills, chariots became less exclusive. Smaller states and less wealthy nobles could afford them. This democratization of military technology shifted power dynamics, allowing smaller forces to challenge larger ones if they had superior chariot forces. Eventually, chariots declined in military importance. Several factors contributed to this. Improvements in infantry tactics, particularly the development of disciplined formations with long spears, made chariots vulnerable. Cavalry, warriors fighting from horseback without chariots, proved more flexible and less resource-intensive. Changes in terrain and battlefield conditions also played a role as warfare moved into more varied landscapes. By the classical Greek and Roman periods, chariots had largely disappeared from European battlefields, persisting mainly in ceremonial contexts and racing. But their impact on ancient warfare was profound, shaping military developments for over 1,000 years. Trade and expansion. The wheel revolutionized trade by enabling heavier loads and faster transport over long distances. Before wheeled vehicles, long-distance trade was severely limited. Merchants could only transport what could be carried by pack animals or human porters. This meant small quantities of high-value goods, spices, precious metals, luxury textiles, were the primary trade items. Wheeled carts changed this equation dramatically. A merchant with an ox-drawn cart could transport hundreds of pounds of goods, grain, pottery, tools, textiles, and other everyday items that were too bulky or low value to trade long distances before. This made regional trade in staple goods economically viable. Merchants could move goods farther inland, no longer restricted to rivers or coastlines. Before wheels, most long-distance transport relied on water, rivers, canals, and coastal shipping. Communities distant from navigable water were isolated, able to trade only what could be carried overland on backs. Wheeled vehicles opened the interior regions, allowing settlements far from water to participate in trade networks. This led directly to the creation of road networks. As wheeled traffic increased, the need for maintained pathways became apparent. Rough terrain, muddy conditions, and obstacles that a pack animal could navigate became serious impediments to wheeled vehicles. Communities began clearing paths, filling depressions, building bridges over streams, and maintaining routes that connected settlements. Some of the earliest roads in Mesopotamia were likely built specifically for wheeled carts, laying the groundwork for infrastructure that would last millennia. These early roads were simple, cleared earth, perhaps reinforced with stones in muddy areas, but they represented a significant investment of community labor. Trade routes emerged, connecting distant cities and cultures. The most famous ancient trade routes, like the Silk Road connecting China to the Mediterranean, depended fundamentally on wheeled vehicles. Caravans of carts and wagons could transport silk, spices, precious stones, and other goods thousands of miles, moving between civilizations that had no direct contact otherwise. These trade routes facilitated more than just goods exchange. They enabled cultural exchange, spreading ideas, technologies, religions, and innovations along trade paths. A merchant traveling from Persia to India carried not just physical goods, but also knowledge, stories, techniques, artistic styles, philosophical ideas. The wheel, by enabling long-distance trade, became a vehicle for cultural transmission. Trade encouraged specialization and economic growth. When communities could reliably trade their surplus production for goods they couldn't produce locally, specialization became economically rational. A region with excellent clay deposits could focus on pottery production, trading their ceramics for grain, metal tools, and textiles from other regions. This specialization increased overall productivity. Rather than every community producing everything at a mediocre level, communities could focus on what they did best, achieving higher quality and efficiency. The surplus could be traded, ensuring everyone had access to a wider variety of goods. Regional economies became interconnected. A drought in one region affecting grain production would impact prices across the entire trade network. A new technology developed in one city would spread along trade routes to distant locations. Economic prosperity in one area would stimulate trade throughout the network, benefiting multiple regions. Urban development accelerated. Cities located at crossroads of trade routes grew wealthy and influential. They became centers of commerce, culture, and power. The wealth from trade-funded monuments supported artisans and scholars and attracted migrants from surrounding rural areas. Roads and infrastructure became crucial to economic success and political power. States that built and maintained good roads gained economic advantages through increased trade. They could move armies faster, improving military capabilities. Good infrastructure attracted merchants and settlers, increasing population and tax revenue. The Romans would later perfect this understanding with their extensive road system, but the principle was established in the Bronze Age. Roads enabled by wheeled transport were investments that paid dividends through increased trade, better military mobility, and enhanced communication across territories. The wheel enabled humans to reshape landscapes. Building roads required cutting through forests, leveling hills, filling valleys, and bridging rivers. Canals were dug to connect waterways, often with towpaths, alongside for animals pulling barges, essentially using wheels on water. This reshaping of landscapes to accommodate wheeled transport represented a new relationship between humans and their environment. We weren't just adapting to the landscape, we were modifying it to suit our technological needs. This pattern would intensify throughout history, but it began with the roads built for wheeled vehicles. Economic and societal impact. Beyond transportation and trade, wheels powered a revolution in mechanical technology that transformed agriculture, industry, and daily life. The principle of the wheel, circular motion around an axis, proved applicable to countless mechanical applications beyond vehicles. Water wheels appeared relatively early, though exact dates are debated. These large wheels were placed in flowing rivers or streams, with paddles or buckets around the rim. The flowing water pushed against the paddles, causing the wheel to rotate. This rotation could be harnessed to power machinery, most commonly grain mills. Water-powered grain mills revolutionized food processing. Before these mills, grinding grain into flour was exhausting manual labor, typically done by hand using grinding stones. A person might spend hours grinding enough grain for a day's bread. A water mill could grind grain continuously, producing flour at rates far exceeding human capability. This had profound implications. Communities with water mills could process grain more efficiently, freeing human labor for other activities. Mills became valuable economic assets, often controlled by local lords or religious institutions who charged fees for their use. Access to milling capability became an important element of economic and social power. Windmills appeared later, probably first in Persia around the 9th century CE, then spreading to Europe during the medieval period. These used the same principle as water wheels, but captured wind energy instead of water flow. Windmills extended mechanical power to regions without suitable rivers, and they could be built in locations optimal for wind, rather than being constrained to riverside locations. Gear systems evolved from wheel technology, allowing rotational motion to be transmitted, redirected, and modified. Gears are essentially wheels with teeth that mesh together, transmitting force from one wheel to another. By using different-sized gears, mechanical advantage could be achieved, trading speed for power or vice versa. These gear systems enabled complex machinery. Mills used gears to convert the horizontal rotation of water wheels or windmills into vertical rotation for grinding stones. Lifting mechanisms used gears to multiply human strength, allowing workers to raise heavy loads with less effort. Clock mechanisms used gear trains to translate the slow, steady power source into the precisely timed movements of clock hands. The wheel boosted agriculture beyond just transportation. Wheeled plows became more effective than simple hand plows or animal-drawn wooden plows. The wheel provided stability and control, allowing farmers to plow straighter furrows and work more land in less time. Irrigation systems used water wheels to lift water from rivers or wells to higher ground, allowing cultivation of land that couldn't be watered by simple channels. These water-lifting wheels, sometimes called norias or sakiyas, were crucial in many agricultural societies, particularly in arid regions where irrigation meant the difference between abundance and starvation. Industry benefited enormously from wheel-powered machinery. Textile production used spinning wheels to twist fibers into thread more quickly and evenly than hand spinning. Later, water-powered spinning machines would mechanize textile production further. But the basic principle of the wheel was fundamental. Mining operations used water wheels to power pumps that removed water from deep mines, allowing extraction of ores from depths that would otherwise flood. Wheels powered bellows for smelting furnaces, improving metal production. Wheels were integral to lifting systems that brought ore to the surface. Construction used wheels extensively. Cranes with pulley systems, wheels with grooves for rope, allowed builders to lift heavy materials to great heights. The great cathedrals of medieval Europe were built using sophisticated crane systems based on wheel and pulley technology. Urban development was encouraged by wheel technology at multiple levels. Cities needed roads for wheeled vehicles, spurring infrastructure development. The economic benefits of trade attracted population growth. Mills and wheel-powered industries provided employment, drawing rural populations to urban centers. Cities became nodes in transportation networks, growing at intersections of major roads or at river crossings where water and land transport met. The wealth generated by trade and industry funded civic improvements, walls, aqueducts, public buildings, and markets. The wheel enabled humans to reshape landscapes on a grander scale than ever before. Roads were built across mountains and through forests. Canals were dug to connect rivers with locks, which themselves used wheel and gear mechanisms, allowing boats to navigate changes in elevation. Terraces were built for agriculture, made practical by the ability to transport materials to construct them. This landscape modification was unprecedented. For the first time, humans were systematically altering the environment to suit their needs rather than simply adapting to existing conditions. The wheel, by making transport and mechanical power more accessible, was a key enabler of this transformation. The wheel in modern times. The principles of the wheel underpin an enormous range of modern technology. The bicycle, invented in the 19th century, uses spoked wheels and represents a direct evolution of ancient wheel technology. Modern bicycle wheels are marvels of engineering, lightweight, strong, aerodynamic, but they operate on the same fundamental principles as Bronze Age chariot wheels. Trains revolutionized 19th century transportation using flanged steel wheels on steel rails. This combination of wheel and rail provided minimal friction, allowing enormous loads to be pulled by steam engines. Rail transport enabled the Industrial Revolution to achieve global scale, moving raw materials to factories and finished goods to markets more efficiently than ever before. Automobiles, perhaps the most visible application of wheel technology, transformed 20th century society. The pneumatic tire, a wheel covered with air-filled rubber, provided a smooth ride and good traction, making motorized vehicles practical for everyday use. The internal combustion engine provided power, but it was the wheel that translated that power into motion. The automobile's impact on modern life cannot be overstated. It reshaped cities, with roads and parking becoming major urban features. It enabled suburban development, allowing people to live farther from their workplaces. It created entire industries: manufacturing, fuel, maintenance, insurance, employing millions. Industrial machines of every type use wheels and circular motion. Electric motors generate rotational motion, which is then transmitted through gears, belts, and pulleys, all wheel-derived technologies, to power everything from factory assembly lines to home appliances. The evolution from wood to iron to steel to rubber tracks, material science progress. Early wheels were limited by wood's strength and durability. Iron and steel wheels were stronger and longer lasting, enabling heavier loads and higher speeds. Rubber tires provided shock absorption and traction, dramatically improving vehicle performance and comfort. Modern wheels use advanced materials: carbon fiber, titanium, specialized alloys, chosen for specific performance characteristics. Racing bicycle wheels are optimized for minimal weight and maximum aerodynamic efficiency. Aircraft landing gear wheels must withstand enormous impact forces. Each application drives specialized engineering. The wheel became a symbol of technological progress itself. We speak of reinventing the wheel to describe unnecessary work, implying the wheel's design is so perfected that improvement is pointless. Industrial Revolution imagery frequently featured wheels, gear wheels, spinning wheels, wagon wheels, representing the mechanization of society. What's particularly interesting is that the wheel is everywhere, even in devices that aren't literally circular on the outside. Gears inside watches, transmissions, and machinery are wheels with teeth. Pulleys are wheels with grooves. Flywheels store rotational energy. Gyroscopes use spinning wheels for stabilization and navigation. Electric motors and generators operate on principles of circular motion. The rotors inside are wheels, spinning at thousands of revolutions per minute to convert electrical energy to motion or vice versa. Without this wheel-based technology, modern electrical power systems wouldn't exist. Computer hard drives use spinning platters, wheels coated with magnetic material to store data. Though solid-state drives are replacing them, spinning disk technology stored humanity's data for decades. Even in the digital age, the wheel remained relevant. Turbines in power plants, whether water, steam, or gas, are essentially wheels with blades that capture fluid flow and convert it to rotational motion, which then drives generators to produce electricity. The basic principle is the same as ancient water wheels, scaled up and refined with modern engineering. The wheel's adaptability is remarkable. The same basic concept, circular object rotating around an axis, has been applied to solve countless problems across 5,000 years of technological development. Each application requires different engineering solutions, different materials, different scales, but the fundamental principle remains constant. Philosophical and reflective points. The wheel exemplifies how simple ideas can have transformative power. The basic concept, a circle that rotates, is easy to understand. A child can grasp it, yet its implications have been vast, touching nearly every aspect of human civilization. This simplicity to impact ratio is remarkable. Some transformative technologies are complex, requiring sophisticated understanding to even conceptualize. The wheel is not like this. Its genius lies not in complexity, but in recognizing a simple geometric shape's utility and engineering it into a practical device. The wheel shows the interplay of observation, experimentation, and adaptation in human history. Our ancestors observed that round objects roll. They experimented with rolling logs to move heavy loads. They adapted this principle, abstracting it, separating the rolling surface from the load, and creating something that didn't exist in nature. This process, observe, experiment, adapt, is fundamental to human innovation. The wheel is an early and clear example of this pattern, which we see repeatedly throughout technological history. From stone tools to spacecraft, human innovation follows this pattern of building on observations and previous innovations. The wheel also demonstrates that innovation often comes from combining existing concepts in new ways. The circle existed conceptually. The axle existed. A straight shaft was used in various tools. The innovation was combining them in a specific configuration where the circle rotates around the fixed shaft. This combinatorial nature of innovation is important to recognize. Breakthrough technologies rarely emerge from nothing. They come from connecting existing ideas or techniques in novel configurations. The wheel combined circular form with rotational mechanics, creating something greater than either component alone. Without the wheel, civilization as we know it might not exist. This is not hyperbole. Consider what the wheel enabled. Efficient long-distance transport made trade networks possible, connecting civilizations and spreading knowledge. Wheeled vehicles enabled agriculture to scale beyond local subsistence. Wheel-powered machinery multiplied human productive capacity. Cities might not have developed to the same scale without wheels to bring in food and materials. The great empires of history depended on road networks for administration and military control, which in turn depended on wheeled transport. The Industrial Revolution relied fundamentally on wheel-derived technologies, gears, pulleys, spinning wheels, locomotives. Remove the wheel from history, and you remove or severely limit many subsequent technological developments. No efficient land transport means no large-scale trade networks. No mills mean slower food processing. No gears mean no mechanical advantage for complex machinery. The cascade effects of not having the wheel would reshape history completely. Yet the wheel seems so obvious in retrospect that we rarely consider how remarkable its invention was. This is a cognitive bias called hindsight bias, the tendency to see past events as having been predictable or obvious. The wheel feels obvious now, but it wasn't obvious for hundreds of thousands of years of human existence before its invention. Consider, the wheel appeared only around 5,500 years ago. Anatomically, modern humans have existed for perhaps 300,000 years. For over 99% of human history, we didn't have wheels. The societies that built Göbekli Tepe, created cave art, and populated the entire planet did so without wheeled transport. Some advanced civilizations never independently invented the wheel. The great pre-Columbian civilizations of the Americas, the Maya, Aztec, and Inca built massive cities, developed sophisticated writing and mathematics, and created complex societies without using wheels for transport. They had the wheel concept. Children's toys with wheels have been found, but they didn't adapt it for transport, possibly because they lacked suitable draft animals. This tells us something important. The wheel's invention required specific conditions and opportunities. It's not inevitable. It required both the conceptual breakthrough and the practical means to implement it. Suitable materials, draft animals, terrain where wheels were advantageous, and social organization to maintain roads and vehicles. The wheel also illustrates how technology shapes society and society shapes technology. Wheeled vehicles enabled new social organizations, empires spanning vast territories, urban centers supporting large populations, merchant classes conducting long-distance trade. But society also shaped wheel development. Military needs drove chariot innovation. Trade demands led to better roads. Industrial capitalism funded railroad development. This bidirectional relationship between technology and society is fundamental to understanding human history. We create technologies that then reshape how we live, which in turn influences what technologies we develop next. The wheel is an early and clear example of this dynamic. Looking forward, the wheel continues to evolve. Magnetic levitation trains use magnetic fields instead of mechanical wheels, yet still move along circular paths and use rotational motors. Concept vehicles experiment with omnidirectional wheels that can roll in any direction. The basic principle adapts to new materials, new power sources, new applications. The wheel reminds us that the most important innovations are often the simplest ones, applied consistently and refined continuously. It's not always about complexity or sophistication. Sometimes the most transformative ideas are the ones that, in retrospect, seem obvious, but took remarkable insight to discover in the first place. Conclusion. The wheel is humanity's great circular achievement, a perfect example of how a simple idea, properly executed, can change everything. From pottery wheels in ancient Mesopotamia to the wheels of Mars rovers, from water wheels powering medieval mills to turbines generating modern electricity. The wheel has been refined, adapted, and applied to countless purposes across 55 centuries. It democratized transportation, making movement of goods and people accessible beyond elite classes. It multiplied human mechanical power through mills and machinery, enabling agriculture and industry to scale beyond what muscle power alone could achieve. It connected distant civilizations through trade routes, facilitating the exchange of goods, ideas, and cultures. The wheel shaped our cities, our economies, our societies, and our understanding of mechanics and physics. It's so fundamental to modern life that we struggle to imagine existence without it. Yet for most of human history, we lived in a wheelless world. Perhaps the wheel's greatest lesson is this: the most transformative innovations need not be the most complex. Sometimes the simplest idea, clearly conceived and skillfully executed, can change the course of history. The wheel, a circle rotating on an axis, is proof that elegant simplicity, applied with ingenuity, can transform the world. As we stand in the 21st century, surrounded by wheels visible and hidden in vehicles and machines and devices of every description, we benefit from an insight first grasped 55 centuries ago. That insight continues to serve us, continues to evolve, and will likely continue far into humanity's future. The wheel rolls on, carrying civilization forward, just as it has for 5 millennia. It remains one of humanity's simplest, most elegant, and most consequential innovations. A perfect circle that moved the world. Thank you for watching.